Hi Narmada. Okay, so today is already 7:02, so let's wait for a few minutes and let's see the numbers will come. So any doubt on specific topics? Like, okay, great. Okay.
Good evening, sir.
Hi, good evening. Today can you hear me properly?
Yes, sir.
Okay. Okay, so today also we'll be solving 4 questions from 2017 and 2016 and 2015 paper. So okay, so let's start. Then in the meantime others will join. Okay. So if you have doubts while solving the question, you can just ask without any hesitation. So you can ask. Is my screen visible?
Yes, sir.
Okay. Okay, so this is question number 46 from 2016 paper. Okay, just. So this is question about the statistical thermodynamics or partition function like this. So the question says, consider a two-state system at thermal equilibrium with equal degeneracy where the excited state is higher in energy than the ground state by 0.1 electron volt, and we have to find out the ratio of the population of the excited state to that of the ground state at a temperature for which kBT equal to 0.05 electron volt. Okay, so so it is said that we have a two-state system at thermal equilibrium. So let's say this is state 1 and this is state 2. So this system is in thermal equilibrium with temperature T. So let's say the energy corresponding to the state 1 is epsilon 1 and energy corresponding to the state 2 is epsilon 2, and the degeneracy corresponding to the state 1 is let's say G, and the degeneracy is equal, so the degeneracy corresponding to the state 2 will also be equal to Z. So so here in this picture G equal to 1, just one state with energy epsilon 1 and epsilon 2. So the partition function for this system, this two-state system, will be partition function. Let's denote it by Z. Z equal to just sum over these two energy states with epsilon e to the power minus ei divided by kBT, like sum over I equal to 1 to 2 exponential minus epsilon I over kBT. So e to the power minus epsilon 1 divided by kBt plus e to the power minus epsilon 2 divided by kBt. So this is the partition function, this is our partition function, and as the system is in thermal equilibrium, all the particles will be distributed in these two states according to the Boltzmann distribution. So the probability of finding a particle, or probability of lying a particle in the lying in the state of energy epsilon 1 is P of epsilon 1 will be equal to just exponential e to the power minus energy of that state, like epsilon 1 divided by kBt divided by the partition function. So this is the expression of probability of finding a particle at state of energy epsilon 1. Okay, so similarly the probability of finding a particle at state of energy epsilon 2 will be equal to P of epsilon 2 equal to just e to the power minus epsilon 2 over kBt divided by z, same partition function for the whole system, two-state system. Now we have to find out the ratio. So the ratio of population, that means the ratio of population of the excited state to the ground state will be equal to just P of epsilon 2 divided by P of epsilon 1 will be equal to just e to the power minus epsilon 2 over kBt. Z partition function will cancel with each other, so it will be e to the power minus epsilon 1 divided by kBt. So e to the power minus epsilon 2 minus epsilon 1 divided by kBt, right? So epsilon 2 minus epsilon 1 is the energy difference between the two states, state 1 and state 2. So it is given here 0.1 electron volt, and the kBt is also given 0.05 electron volt. So you have to just put these values here, 0.1 electron volt divided by 0.05 electron volt. So the population ratio will be just, let me just calculate this, minus 0.1 e to the power minus 0.1 divided by 0.05. Which will be equal to 0.135. So this is the population ratio. So the population ratio of the excited state to that of the ground state at a temperature of kBt equal to 0.05 electron volt will be just 0.135. Okay, so this is actually pretty simple. So I hope everything is clear regarding this question, right?
Service.
Yeah, okay. So let's just move to the next question. Just a second. So next question is question number 47 from the same 2016 paper, and this is question about the IR activity of different vibrational modes. So the question says the of the following vibrational modes given below, the IR active modes is or are. So this is the three vibrational modes, so vibrational normal modes of CO2 molecule. So CO2 is the linear molecule. Now we have to find out which of the following modes are IR active. So basically there are three modes given. First one is this is the symmetric stretching mode. Symmetric stretching matlab this CO bond, this one of the CO bond and this CO bond actually stretches and compresses equally by equal amount. So that's why we are calling it symmetric stretch. And the second one is the asymmetric or antisymmetric stretch, because they are stretching or compressing by unequal amount by, so that's why we are calling antisymmetric or asymmetric stretches. And the third one is bending mode. So for any vibrational mode to be infrared active, so they have to satisfy some properties like the motion corresponding to that vibrational mode, the dipole moment, the change of dipole moment has to be non-zero, like change of dipole moment has to be non-zero. Like for IR spectroscopy, for any vibrational mode to be in IR spectroscopy, for any vibrational mode to be IR active, so the change of dipole moment corresponding to that mode has to be non-zero. So molecule, the whole molecule can be non-polar, but change of dipole moment for any given vibrational normal mode has to be non-zero. So for example, like for this CO2 case, the molecule is a linear molecule, right? So that means for this CO bond, the dipole moment direction is like this, from positive carbon end to negative oxygen end, and for this bond the dipole moment direction is like this. So as a whole, the molecule is the dipole moment of the carbon dioxide molecule is zero, right? Because the dipole moment is a vector quantity. So one vector pointing in this direction and another vector is pointing completely opposite direction and by equal amount. So that's why if you just take the resultant of these two vectors, the angle is 180 degree, so the resultant vector will be zero. So that's why the dipole moment of the linear CO2 molecule is zero. But for like option 1, for the symmetric stretch case, let's calculate the change of dipole moment. Why change? Because this is a particular vibrational normal mode, right? So that means all the atoms will be in motion, will be moving. So that's why we are calculating the change of dipole moment for during the motion. So for the symmetric stretch case, this CO bond actually let's say due to the stretch or compress, the dipole moment direction is like this, and this CO bond stretches or compresses by equal amount and in opposite direction. So the dipole moment direction will be exactly equal in magnitude but opposite in direction. So that's why the change in dipole moment, so let's denote is del mu del x. What do this quantity mean? Del mu del x is the change of dipole moment with respect to the coordinate. So let's say this is coordinate x. So the change of dipole moment with respect to coordinate is 0 in this case. Why? Because for one CO bond the dipole moment direction is one direction, and for another CO bond the dipole moment vector is equal in magnitude and opposite in direction. So that's why the resultant vector for that motion will be 0. So that's why the option 1 for the stretching mode is IR inactive mode. Now let's move to the option 2. Option 2 is the antisymmetric stretch. Why antisymmetric stretch? Because this is actually not antisymmetric. So because the C double bond O bond here stretches in this direction while stretching, and this C double bond O bond also stretching in this direction. So the molecule will look like this, like oxygen atom is moving in this direction and this oxygen atom is also moving in this direction. So if we just calculate the change of dipole moment due to this motion, so the dipole moment due to the motion of this CO bond will be, dipole moment direction will be this direction, and for this CO bond will be this direction for the stretching case. So that's why there is a net dipole moment here. So there is a net change of dipole moment here. So del mu del x will be equal to not is equal to 0. Why not is equal to 0? So let's just because due to the motion of this CO bond, the dipole moment changes in this direction, but with a larger amount, and for this CO bond the dipole moment changes by least amount. This is actually moving, but by least amount it is moving by least amount compared to this bond. So this is also the dipole moment direction is directed in this direction, but this magnitude of this dipole moment is small compared to this dipole moment. So that's why there is a net dipole, we will get a net dipole moment. So the change of dipole moment due to this motion will be not is equal to 0. So that's why the antisymmetric stretch mode will be IR active mode. And the bending mode, okay, if we just calculate the change of dipole moment due to the bending motion, so the oxygen atom is moving in this direction, both oxygen atom are moving in this direction, and the carbon atom is moving in this direction. So when this oxygen atom is moving, so let's just draw a snapshot type thing. So this is just a snapshot. So while both this oxygen atom is moving in the upward direction and the carbon atom is moving in the downward direction, right? So if we just calculate the change of dipole moment while during the motion, so the dipole moment for this CO bond will be directed this direction, and the dipole moment for this CO bond will be directed along this direction. So if we just compute the resultant dipole moment vector, so there will be a resultant dipole moment vector looks like this. So we will get a dipole moment value as dipole moment value during the motion, during the bending motion. So that in this case also the del mu del x will be not is equal to 0 due to the motion itself, not the molecule, due to the motion. So that's why this bending motion is also IR active. So following out of the following three modes, the option 2 the antisymmetric stretch, and the option 3 the bending vibrational bending motion will be IR active. So the option D is the correct answer, 2 and 3. Now just the take home message is that here for IR spectroscopy, for any vibrational normal mode to be IR active, you have to check the change of dipole moment due to that corresponding motion. So you have to calculate the del mu del x. If this change of dipole moment, that means del mu del x, is not is equal to 0, then the respective mode will be IR active. If the change of dipole moment, or let's say del mu del x, is 0, then the corresponding or respective vibrational mode will be IR inactive. The whole molecule can be non-polar. Like in this case, the CO2, the linear molecule, whole molecule, the dipole moment of the whole molecule is 0. But in IR spectroscopy, the change of dipole moment due to the motion will matter. But in rotational spectroscopy, this is vibrational spectroscopy, right? IR spectroscopy is vibrational spectroscopy, and in rotational spectroscopy, the molecule has to have a permanent dipole moment. So it has to have that means mu has to be not is equal to 0. So that's why for CO2 case we cannot have any peak in the rotational spectroscopy. So for rotational spectroscopy, this is important. The molecule has to have a permanent dipole moment. That means mu not is equal to 0. Because in more fundamental case, in spectroscopy, we just apply an external electromagnetic field, right, to the molecule. Now that external electromagnetic field has to interact with the molecule, different molecular motion. Let's say in vibrational spectroscopy, the external electric field is infrared radiation, and infrared radiation will interact with the vibration of the molecule. Now the external electric field will interact with the change of dipole moment due to the vibration. And in rotational spectroscopy, the external electric field is the microwave radiation. Microwave radiation, and this microwave radiation will interact with the molecular rotational motion, but the molecule has to have a permanent dipole moment. Why? Because let's say the first molecular dipole moment vector looks like this. This is a dipole moment vector of the whole molecule. Let's say for a water molecule. Now while rotating, this dipole moment vector will also rotate, right? Let's say first it will rotate like this, then it will rotate like this, then it will rotate like this, then again it will rotate like this. So that's why the rotation of the permanent dipole moment vector will look like a sine wave. So this will interact with the microwave radiation. So that's why the molecule, having permanent dipole moment is very important in this case. Okay, so back to the question. So in this question, the option D, that means the option 2 and option 3 is IR active mode. Oh sorry, so my internet was disconnected. So where we actually, so did we solve this question or not? Anyone? So did you completely solve this question after? Okay, sorry for that. Okay, so the question is about the which of the question is, out of the following three vibrational modes, of which of the modes are IR active? So for in IR spectroscopy, for any vibrational mode to be IR active, the change of dipole moment has to be non-zero. The dipole moment of the whole molecule can be zero, like the molecule can be non-polar as a whole, but the change of dipole moment during the motion of any particular vibrational mode has to be non-zero. So for vibrational mode to be IR active, we have to check the del mu del x, that means change of dipole moment due to the particular motion is zero or not. So let's first analyze the option 1. So option 1 is the symmetric stretch of the CO2 molecule. Symmetric stretch means the change of dipole moment here. So the dipole moment corresponding to this mode, this CO bond is directed towards this direction, and the dipole moment corresponding to this CO bond is directed towards this direction. So due to the symmetric stretch, the dipole moment, both the dipole moment directions are equal in magnitude and opposite in direction. So these dipole moment vectors are equal in magnitude and opposite in direction for the symmetric stretch. That's why the change of dipole moment due to the symmetric vibrational motion is zero. So the change of dipole moment for the symmetric vibrational motion is zero. So that's why this mode is IR inactive. Now the second option is the antisymmetric stretch. Now the dipole moment corresponding this CO bond is directed towards this direction, and the dipole moment corresponding to this CO bond will be directed towards this direction. But due to the antisymmetric stretch, the magnitude of the dipole vector will be different. So if we calculate the change of dipole moment due to this antisymmetric vibrational motion, we will get a net dipole moment during the motion. So that's why the change of dipole moment del mu del x here is not is equal to zero in this case. So that's why this mode will be IR active mode. And let's come to the bending motion. So this is bending motion, option 3, and in this case also the oxygen both the oxygen atom are moving in the upward direction and the carbon atom is moving in the downward direction. If we just draw a snapshot type of thing, so one snapshot is the oxygen atom looks like this. So for this case, the dipole moment vector corresponding to this bond will be like this, and the dipole moment vector corresponding to this CO bond will be like this. So during the motion, during the bending vibration, we will get net resultant dipole moment vector which will look like this. So that means we will get del mu del x, that means change of dipole moment during the bending vibration is not is equal to zero. So that's why this bending motion will be also IR active mode. So to answer this question, the option 2 and 3, vibrational mode number 2 and 3 will be IR active mode, and the symmetric stretch mode will be IR inactive mode. So option D is the correct answer. Now just to remember one thing, just in IR spectroscopy, for any vibrational mode to be infrared active, we have to check the change of dipole moment during the motion, during the particular vibrational motion. Change of dipole moment, that means del mu del x has to be not is equal to 0 for any vibrational mode to be IR active, and the change of dipole moment if 0, then the corresponding mode will be IR inactive. Okay, the dipole moment of the whole molecule can be non-zero, like for the CO2 case, CO2 is non-polar molecule. But in a rotational spectroscopy, the molecule has to have a permanent dipole moment. That means the total dipole moment of the molecule, let's call it mu, has to be non-zero in a rotational spectroscopy. Okay, so any doubt regarding this question?
No, sir.
Okay, sorry for the internet actually. Okay, so let's just move to the next question. Okay, so this is question number 14 from 2015 paper, and the question says, for an ideal gas with molar mass capital M, molar translational entropy at a given temperature is proportional to which of the following option? So molar translational entropy, so translational entropy, is to calculate the translational entropy we have to first calculate the translational partition function. So for an ideal gas of molar mass M. Okay. So for an ideal gas system, we just model. So let's say that for a system, so this is a cubic box and with full of ideal gas molecules with a molar mass M. So we just model this system as particle in a box, 3-dimensional box, particle in a 3D box. Okay, so we know the energy eigenvalue corresponding to the this problem. So epsilon will be equal to just 8 capital M divided by nx square by Lx plus ny square divided by Ly plus nz square divided by Lz, right? Here nx, ny, nz are the quantum number along the x, y and z direction, and allowed values of nx, ny, nz will be just 1 to infinity. The 0, nx equal to 0 is not allowed, ny equal to 0 is not allowed, and Lx, Ly, Lz are the length along the x, y and z direction, length of the box. Now if partition function means, so partition function for this problem will be just if we sum nx equal to 1 to infinity, ny equal to 1 to infinity, nz equal to 1 to infinity, and epsilon to the power minus epsilon x, y, z divided by kbt, right? So this is the formula partition function, sum over all possible energy states. So if we just do this, nx equal to 1 to infinity, ny equal to 1 to infinity, and nz equal to 1 to infinity, we can separate this. We can just write this term like h square divided by 8m nx square by Lx kbt, like this. It minus h is 8m ny square by Ly kbt, and minus h square by 8m nz square by Lz kbt. So these are independent, so we can separate this whole term. So nx equal to 1 to infinity e to the power minus h square by 8m nx square by Lx kbt. Like this, there will be a y term and there will be a z term. So if you just take this term, let's just call it Sx, sum over x. So Sx is this sum over nx equal to 1 to infinity e to the power minus h square over 8m nx square by lx kbt. Now just if this sum, let's write it down first, nx equal to 1 to infinity e to the power minus h square nx square 8m lx kbt. So let's just write nx equal to 1 to infinity e to the power minus, let's call it alpha 1. So alpha 1 is h square by 8m lx kbt. Now we can convert this sum to integration like 0 to infinity e to the power minus alpha 1 nx square d nx, when alpha 1 is very less than of 1. So in this condition we can convert this sum to this integration sign. So alpha 1 means alpha 1 very less than 1 means h square by 8m lx square so there will be lx square here. So very less than of kbt. This condition means the energy difference between the two states has to be very less than of thermal energy. So in this condition we can convert this sum to integration. So this is actually Gaussian integration. We can perform the Gaussian integration, just half of root over pi over alpha 1. So if you just do this, you will get Lx divided by, let's call it lambda d, where lambda d is the h over root over 2 pi m kbt. So S1 will be just Lx divided by lambda d. Here lambda d we call it thermal de Broglie wavelength. So this will be needed to solve other questions. Thermal de Broglie wavelength has the expression h over root over of 2 pi m kbt. So lambda d is proportional to 1 upon root over of temperature. Lambda d also proportional to 1 upon root over of m. Okay, now for 3-dimensional case, the total partition function z is s1 times s2 times s3, right? So if we just multiply this xx sy ly lz divided by lambda d cube. So lx ly lz means volume of the cube box, so v divided by lambda cube. So this is the translational partition function. So z equal to v divided by lambda cube. Now we can just compute the energy translational entropy from this partition function itself. How that means, so we know E equal to A minus Ts. A is the Helmholtz free energy, S is the entropy, E is the energy, that means internal energy, T is the absolute temperature. So S will be equal to E minus A divided by T. So E will be equal to, we know okay, so this is the single particle partition function Z. Now if the particles are indistinguishable to each other, the n particle partition function Zn will be single particle partition function to the power n divided by n factorial if the particle are indistinguishable to each other. So the energy, we can calculate energy equal to kBT square del ln Zn divided by del T constant V and N. So this is the expression for calculating energy. So energy is kBT square del ln Zn del T constant V and N. So just if you just put Zn equal to Zs kBT square, Zn equal to Zs to the power n divided by n factorial del T. So it will be just kBT square del T of n ln Zs minus ln n factorial. So this is actually temperature independent, so this term will be 0. So the final term will be kBT square del, so n kBT square del ln Zs by del T. Similarly, we can compute Helmholtz free energy A minus equal to kBT ln Zn. So that will be just minus n kBT ln Zs plus kBT ln n factorial. So S will be equal to E minus A over T. So if you just compute this, you will get n kBT del ln Zs by del T divided by T. So n kBT square divided by T, that means n kBT plus n kb ln Zs plus this term will be there minus k minus kb ln n factorial. So if you just put this Zs here, this Zs and this Zs, and if you just approximate ln n factorial with n ln n minus n, you will get the final expression of S, which is equal to just n kb ln V over n. V is the volume of the cubing box, plus 5 by 2 1 plus 3 by 5 ln 2 pi capital N kBT divided by h square, like this. So this is the final expression of entropy from indistinguishable ideal gas particles, and this is called the Sahut tetrode equation. You know this Sahut tetrode equation is a CHEY Now from this expression you can get the answer, like entropy is proportional to ln m, right? So for an ideal gas with molar mass m, the molar translational entropy at a given temperature is proportional to ln m. Okay, so now let's just move to the next question. So this is question number 20 from 2015 paper. The question is the ease of formation of the adduct NH3 and BX3, where X equal to halogen element fluorine, chlorine and bromine, follows the which of the following order. So adduct is here NH3, NH3 BX3, right? So here NH3 is the Lewis base. Why? Because the structure of NH3 ammonia is, it has the 3 hydro NH bond and 1 lone pair is available here, and the BX3 is Lewis acid because it has this structure, and boron atom has an empty p orbital, pz orbital, let's say. So let's say this is z direction. So boron atom has empty pz orbital. So the adduct means this is a Lewis acid Lewis base complex formation. Now the nitrogen lone pair will give its lone pair to the empty p orbital or pz orbital of the boron and will form a weak adduct or Lewis acid Lewis base complex. Now the adduct formation will form, this adduct or Lewis acid base complex will form easily if the energy corresponding to this lone pair of nitrogen and the pz orbital are similar to each other. That means if the pz orbital is vacant, so then the nitrogen lone pair will easily donate its lone pair of electron to the empty pz orbital and the adduct will form easily. Now interestingly, for the X equal to C8 case, that means fluorine BF3, let's first draw the structure. So fluorine has also full filled 2pz orbital. So the fluorine filled electron from the 2pz orbital will also form bond, double bond with the boron empty 2pz orbital. So this bonding is called the back bonding. So this filled electron here will also donate this electron to this empty pz orbital and will also form a partial double bond character like this. So this bonding is called back bonding. So due to this, the initial empty pz or 2pz orbital of the boron is now partially occupied. So the BF bond will also gain partial double bond character. Now the back bonding will be easy when the energy of this empty orbital and the filled orbital are similar. Then they will interact more strongly. So the 2pz or so this is fluorine has filled 2pz orbital and boron has empty 2pz orbital. So both 2pz orbital can interact strongly, overlap strongly. So that's why the back bonding is strong in the BF3 case. Now in X equal to Cl, that means BCl3 case, chlorine has 3pz orbital, right? Like it has 3pz orbital and boron has 2pz orbital. So the structure of 3pz orbital is larger compared to the 2pz orbital. So that's why the overlap between these two filled and empty orbital is not so that much. So that's why the back bonding is not strong compared in BCl3 case compared to the BF3 case. And also X equal to X equal to bromine case, BBr3 case, the bromine has 4pz orbital and the boron has 2pz orbital, and 2pz 4pz is also, the overlap or interaction is not strong, it is weak interaction because of size mismatch. So that's why the back bonding is also weak in this case. So in BBr3 case, the boron has most emptiest 2pz orbital, right? Because the bromine atom, bromine electron cannot donate this electron to the boron empty boron 2pz orbital. So that's why the boron has the empty 2pz orbital in BBR3 case most. So that's why the NH3, the lone pair electron of the nitrogen can donate its electron easily to the empty 2pz orbital of the boron. So that's why the NH3 BBR3 adduct will form easily, then the NH3 BCl3 adduct, then NH3 BF3 adduct. So the order will looks like this: BF3 less than BCl3 less than BBR3. So the option C will be the correct answer in this case. Okay, so any doubts regarding these 4 questions?
No, sir.
Okay. Okay, so then I think we'll meet in the next week. Okay, my email ID. Okay. Okay, so did you get that, Narmada? Yeah. Okay, thanks. So if everything is clear, then we can meet in the next week. Is it okay?
Thank you, sir.
Yeah.
Yes, sir. Thank you, sir.
Thanks for joining. Yeah, bye.